Okay, so what I want to do first is just kind of walk you through how to calculate your grade so far. Um, had a few emails about that. And so this is from the syllabus. So this is on Blackboard, this Word file here. And so it's got all the cutoffs for you. And probably the most complicated one is homework because you've had some assignments on Connect, and then you've got the three practice midterm homework assignments that are on Blackboard. And so what you want to do is just average all of those together. So, maybe take what's your percentage from the Connect grade book and then add it together or average it together with whatever is just in Blackboard for your practice midterms. Okay, so let's say, the first one you got 90 something, uh, the second one you got 81, and then the third one you got 85 or something. And then your connect is around 86. And so you average everything together and you get 87%, let's say. Okay, so that's all of your connects plus your practice midterms. And you just take that as a percentage. So it's worth 15%. And so you do 0.87 times 15 and you get so many points for that. Okay, and then the next category is class participation. And, balancing equations worksheet. Yes, that will. Yep. Yeah, good point. Yeah, was there anything else in there? I think I forgot about that worksheet. Yeah, so you average that together as well. Yeah, I don't think there was anything else, but yeah, I totally forgot about that. But yeah, that as well. And that's I think on Blackboard. Do you have a grade in there in Blackboard for that?
Yes, we do.
Yeah. Okay. Good. Okay. So that should be fairly easy to add in there. And yeah, so all that together, and then you'll get so many points for homework, and then everyone will get 5 points for participation. Okay, so you can just add that in, and then your lab reports. We only did, I don't know, two or three or something like that. I'm looking for one more related to energy, which is the topic of the next chapter. And so I thought a good way to do this next chapter would be on Monday, that you'll do a virtual lab, and be a real simple kind of write up for that. But as if you want to calculate your grade right now today, just average all of your lab report grades that again should be on Blackboard, and then there'll be this one more that you'll average in. And so let's say all those come to 92%, so then it's 0.92. And again, your labs are worth 15, so just times 15, and you get so many points. And then each of your midterms, it's after the curve. I don't know, I don't think I curved all of the exams because I think the averages are pretty good, but this last one for sure had a hefty curve. And so it's your percentage after the curve, okay, for all of these, if there is a curve. And then it's just, each of them are worth 15 points again. So it's 0.82 if you got 82%. And you get so many points for these, okay? And so then, once you have all those categories, you just add them up, okay? So you just add it up. That's what you had for homework, participation, your lab, and then your three midterms. And you'll get something, totaled for that. And so far, it'll be out of 80 points because you still have to take the final exam, which is 20%. And so you just do that over 80 and you get a certain percentage and then just read it off the cutoffs. Okay. And so just, so that you're aware too, I was fairly generous last year with the cutoffs. So, for instance, if you were, I don't know, like 86.7 or something like that, I boosted it up to an A minus, so if you're, I'm not as um, hardcore as I am maybe in some of my other classes, and especially this semester with all this crap going on, I'm going to be pretty lax about these. Okay, um, so I'll be doing a lot of rounding in these grade cutoffs as well. Okay, so does that clarify things with like how to calculate your grade so far? Okay, any other questions about that?
Can you explain where you got the 80 points from?
Yeah, so that's what we have done so far is all of these ones. So it's worth, 80 points because you still have 20 left to go. And the whole thing is out of 100%. Okay, because you don't know your final exam grade yet. And that'll be your other 20. Does that make sense? So
Yes, thank
yeah,
you.
yeah. So that's really like thus far is 80 points. And then, of course, whenever have your final exam grade, then it'll be out of 100. Okay. All right. So then, so the final exam, um, I wanted to make it open book, but with the lockdown browser, you won't be able to open up if you have an ebook. And so I figured, the best way to do it is just to let you jot down whatever you want, from notes for whatever on a piece of paper. And so I'm thinking of, like a single sheet, a single, white sheet of paper, 8.5 by 11, both sides. So you can jot whatever you want and refer to that on the final exam. Okay. And then, during that webcam check, I'll have you, you know, put that on the screen somehow. I don't know, as you're panning around with your webcam, or, if you want to hold it up, with you as it's taking a picture of you or something. But just, kind of show me, that you don't have a stack of, 10 pages or something like that. Okay. Okay, so does that clarify things? Does that make you breathe a little easier, hopefully? Okay. All right, and I didn't want to, um, I guess a lot of you are shell shocked from the last exam too, so I didn't want to, forge ahead onto a new topic right away today. So today is going to be, fairly short. I just wanted to go through the exam with you guys so that, you can ask questions about any of these, okay, and really show you, how to work these out, okay. And so this is I guess I can take this one off here. Word. Okay. All right. So this is the first question, and it was related to this reaction here. Okay, and it's already balanced for you. Just do a quick check to make sure. So 10 fluorines and 10. Okay, so yeah, so it's balanced. And so then how many moles of ammonia are needed to react completely with 13.6 moles of fluorine? Okay, and so this one, it's an easier question because you don't have grams that you're starting with. And so it's just really going to be that ratio. Okay, so, fluorine to ammonia is your 5:2 ratio. Okay, so if you have 13.6 moles of fluorine, then how many moles of ammonia? Okay, so really you're just multiplying 13.6 by 2/5. Okay, or in other words, you're dividing by 5 and then multiplying by 2. Okay, so let me do that. So 13.6, hopefully it's that answer, is 5.44. Yeah, okay. This one, argon, which comprises 1% of the atmosphere, and it's approximately 27 times more abundant than carbon dioxide, but it doesn't contribute to global warming. And so this is taking into account that, remember, global warming, it's all about absorption of IR radiation. Okay, and so for that you need actual bonds. Okay, so stretching or bending. Okay, so CO2, remember, if you have this kind of stretching, so the asymmetric stretching, this will absorb infrared radiation. Whereas if you just have individual argon atoms, there are no bonds to absorb infrared. Okay. Okay, this one, calculate the mass of so many molecules. And so whenever you have a number of something, you're going to have to use Avogadro's number somehow. And so this is 2.5 times 10 to the 4. You divide by Avogadro's. And so that will give you the moles. That divided by 6.2, so that is 4.15 times 10 to the minus 20 moles. Okay, and then we want to know the mass. Okay, and so here, I think what tripped up maybe a few of you is nitrogen gas is diatomic, right? So we have to multiply it by 28 grams per mole instead of 14. Okay, so that times 28 is your 1.16 times 10 to the minus 18. Okay. So I guess this one, 5.8 times 10 to the minus 9, that is just for N. Okay, so remember those molecules that have to be diatomic. Okay. Okay, so this one, the shape or geometry of pH 3. And so what's the first step that you need to do for that? Okay, so shape, yeah, very good. So you have to count the valence electrons. So phosphorus is in group 15, or 5A, so there's 5 for that. And then hydrogen, there's 1 and then 3 hydrogens. Yeah, okay, so I thought I did something wrong. So 8 valence electrons. Okay, so then put phosphorus in the middle. Like that. Okay, so then we've placed 6, 7, 8. Okay, so remember that hydrogens are happy with just 2 electrons next to them. Okay, so this one then, that's the Lewis structure. And so it's that structure where you've got AX3L, if you will. Okay, and so that's going to be trigonal pyramidal. Okay, AX3, just like this one, for instance. Okay, that is going to be trigonal planar. Okay, so trigonal pyramidal is if you've got a lone pair on the central atom. Okay, then the molar mass of ethanol, so you're just adding these up. So you got 12 times 2, 1 times 6, and then another 16. Okay, so adds up to 46.1-ish. Okay, so 16, 6, and another 24. So that's 46. Okay. This is just kind of a definition. So free radicals. So these are examples of a couple free radicals. They are highly reactive, so that's true. And they're species with unpaired electrons, like this. Okay, so all of those correctly describe free radicals. How do mineral nanoparticles, like that, whoops, just zinc oxide or titanium dioxide, for instance, how do they protect from UV radiation? So they just absorb infrared radiation. This one, how many atoms? So that's going to tell you somewhere along the line you're going to need Avogadro's number. Okay, so if you have 0.375 moles, again, it's a little easier. You're not starting from grams, so you're already at moles, so you just multiply by Avogadro's. Okay, so that's 6.02 e23 times 0.375 is this 2.26 times 10 to the 23rd. Okay. How many grams of oxygen are needed to react completely with 200 grams of ammonia? Okay, and so this one, you need to calculate moles. Okay, so if you're given this, you can convert it to moles just by using the molar mass, okay, or molecular weight. And so that's 200 divided by, what is it, 14, so 17 grams per mole. So that's for NH3. Okay, so 200 divided by 17 gives you 11.76 moles. Okay, and then how do I calculate moles of oxygen? So this is for NH3. Okay, you're going to use the ratios, right? So you're going to multiply by 5/4. Okay, so in other words, like you could say divide by 4 and then multiply by 5. Okay, so that is times 5 divided by 4. Okay, so that is 14.71, we'll say, moles of oxygen. Okay, and then to get grams, you're going to multiply by this molar mass. So that's, what, 32 grams per mole. Okay, so that's 470 grams. Okay. How many molecules of molecular oxygen? Okay, so this is, yeah, so in words here. So you've got molecular oxygen reacts with 4 molecules of ammonia to form 4 molecules of nitrogen monoxide and 6 of water. Okay, and so it's asking, to balance this essentially for oxygen. Okay, and so, your nitrogens are balanced, your hydrogens, and so you have 10 oxygens over on this side, right? You've got 6 and another 4, so that means you need 5 in front of here. Okay. Predict the shape of nitrous oxide, and then I tell you kind of the order of it. And so for this, again, shape, you're going to have to do the Lewis structure first. And so how many valence electrons do we have? So you're counting up 2 nitrogens and 1 oxygen. Yep, so 16. Okay, so then let's put it like this. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so then you look at this structure. So why is this not the best Lewis structure? For this question, it really didn't matter, really. So if you just got this, you'll get the same answer, right? So you've got a structure where there's no lone pairs in a central atom, so it's still going to be linear. But there is a better Lewis structure because this nitrogen doesn't have an octet. Okay, so it doesn't have an octet. So the way we do that is this, and we can do it over here. Okay, so now we have an octet, okay, for everything. And so this is a better Lewis structure, but it gives you the same shape, right? Both situations, you have 2 atoms bonded to a central atom with no lone pairs. This is your like AX2 variety, okay? So I guess that's the beauty, I guess, of VSEPR determining shapes. You don't have to have the exact best Lewis structure for it, and you'll still get the right shape, okay? Because it's all governed by, you know, lone pairs and bonding pairs around the central atom. Okay, so just kind of a definition. So, you know, so that has 2 electrons. That has 4. And that has 6. Okay, so any line is 2 electrons. Okay. The ozone layer, so just a definition. So it's located in the stratosphere. Okay. You can have ground level ozone, but that's not the ozone layer. Okay. This one, the oxygen molecule. Okay, so a hint here was draw the Lewis structures. So that's ozone, and it breaks apart at lower wavelengths than ozone. Okay, so those are the 2 Lewis structures for ozone versus oxygen. Okay, and so what you can see is that you've got a double bond in oxygen versus this. Remember, it's a resonance form, so you could say this. All these dots here. Okay, so it's kind of between like a 1.5 bond order. Okay, or between a single and a double. Okay, versus this is a double bond. Okay, so this is a stronger bond. Okay, and therefore it's going to require more energy to break. Okay, so more energy means a lower wavelength. Okay, so shorter wavelength. All right, the carbon cycle. So it's just, you know, movement of carbon, and it's through organisms, atmosphere, earth, and the sea. Okay, so all of those sinks for carbon. Okay. UV index forecast of 6.5. So kind of, you know, from the reading, a UV index, it's not high enough, you know, like 14 or a huge number that, you know, all precautions must be taken, and it's not low enough, like 0 or something, and so it's kind of, you know, the only choice. You know, this is never a, this doesn't sound like, you know, a true recommendation. Sunglasses, maybe a hat. Okay, so that should have been kind of a flag. That's probably not right. All precautions, it's not that high of a value. And so really the only one that made sense here is that. Okay, so just reduce your exposure and put on SPF sunscreen. Okay, and so you'll notice that for most of the forecasts. Okay, even when it's in the like 3, I think any time it's greater than 3, it's kind of put on sunscreen and reduce exposure. Okay. The ozone hole, so just a definition question. So it's most prominent over Antarctica. Okay. Ozone. So if we look at the Lewis structures, you remember it has resonance. Okay, so these two. And so that means that each of the bonds are somewhere between a single and a double. So they're going to be equivalent, right? So remember, I showed, I think when we were face to face yet, that those two resonance forms could be described as this. Right, where all those, these bonds are actually equivalent. Okay, and so it looks something like that. Okay, this would be if you only have one resonance. Whoops. Okay, so it's bent. Yeah, it's not linear, so that doesn't make sense. And this one would only be the case if you had one resonance form. Okay, so this is for ozone molecule. Okay, that incorporates both. So it incorporates both resonance forms. Okay. Lewis structure for acetic acid. And so the bond angle of the OCO, so it's actually talking about this one here. So that angle. Okay, and so if you look at this central carbon, that carbon is bonded to 3 things. Okay, and there's no lone pairs on the central carbon. Okay, so this would be our AX3 type of geometry, so it's going to be more like this. Okay, where it's 120 degrees, all these angles. Okay, or trigonal planar is the geometry. Okay. And then the South Pole versus the North Pole. You've got those PSCs, or polar stratospheric clouds. Okay, so that's what really gives rise to the ozone depletion problem. Is you've got these clouds, and then you've got things like HCl and all these chlorinated species that kind of attach onto these ice crystals. And then, through these catalytic reactions, it breaks apart ozone into oxygen and like an oxygen radical. Okay. Effective absorption of IR radiation, and so it's all about vibrations. Okay, it doesn't have enough energy to break apart. It has more energy than required for rotation, so that's microwave, is rotations. And then it excites bonding electrons. That's something more on UV as well. Okay, so all it can do is just vibrate. Okay, bend and stretch. Relationship between chlorine and ozone. Okay, and so remember there was that one chart in the textbook that showed, as the chlorine concentration went up, then the ozone concentration went down. Okay, and so there was that direct correlation. Okay. which does not contribute to global warming. So it's nitrogen. Okay, so again, remember this is all about, again, IR absorption. And so if you have nitrogen, which is this Lewis structure, there's no way that that can stretch or bend so that you change the charge distribution. Okay, so remember CO2 could stretch, whereas this is maybe going out, these are going in. Okay, and that's the mode that will absorb IR radiation. Okay, and so virtually any other molecule can absorb infrared radiation. Okay, so even CFCs as well. Okay, they can. Okay, but nitrogen, any of these, or argon, or anything else like that, oxygen just by itself, okay, can't absorb infrared radiation, which contributes to the ozone hole. Okay, so these ones are responsible for climate change. Okay, so these give rise, to either increased CO2 concentration, okay, loss of forests. So again, there's less to sequester the CO2, okay, but this one is directly responsible for the ozone hole. Okay, so these chlorinated compounds give rise to this trend. Okay, as you pump more chlorine in the atmosphere, then ozone goes down. Okay, so it's really two different effects, right? There's this climate change, which deals with kind of CO2 is the big one, although water is also a greenhouse gas, so it's really related to like greenhouse gas effects. And then the ozone hole is related to chlorinated and brominated, so also these ones, okay? But if you have these compounds that decompose to give you these radicals, then that will destroy ozone, okay? So a different a situation or problem, I guess. Okay. On average, cloudy nights are warmer than clear nights. Okay, and so clouds are composed of water vapor, and water is a greenhouse gas. Okay. Lewis structure. Okay, so this one, HCl, we have 8 valence electrons. Okay, so 2, 3, 4, 5, 6, 7, 8, like that. Okay, and then this is written just a little more explicitly where these 2 electrons are those bonding ones. Okay, which is the best Lewis structure for acetylene. So C2H2 is like that. So we've got 4, so 8, so 10 valence electrons. Okay, so showing the connection here. And so we have 1, 2, 3, 4, 5, 6. So you could say like 7, 8, 9, 10, maybe. And then you see the carbon doesn't have a octet. Okay, and so the way to do that would be, let's say that. Okay, but it's still not satisfied, so then you do that. Okay, and so now each carbon has an octet. All right, and that is the proper Lewis structure. Okay, so if you look at all these, this, again, the carbon doesn't have an octet, so that can't be right. This one, it doesn't have an octet. And then this one, I think it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. Okay, so that has too many electrons. Okay, we only need 10. Okay. Which process is the most important role in the greenhouse effect? And so it's really that energy that is, um, coming. If I draw it like this, I guess. So energy that is being emitted from the Earth's surface is being trapped by our atmosphere. Okay, so it's radiated by the Earth and it's absorbed by the atmosphere. Okay. Which region of the UV spectrum is absorbed least by the atmosphere? Okay, so remember so UVC is the most energetic, and that is really 100% absorbed because it reacts, right? So it's the one responsible for this. Okay, and this one. Okay, so it even will break apart oxygen as well. Okay, so because of this, it's 100% absorbed. UVA is the least energetic. Okay, so it is the least absorbed. Okay. And then HFCs, this is just from the reading, so HFCs were, remember if you had this as a CFC, fluorocarbon, we'll say that one, for instance, this is a CFC, a chlorofluorocarbon. A HFC is just replacing the chlorine with hydrogen. Okay, so it still has fluorinated carbon, but now it's got hydrogen in its place. Okay, so they don't contain chlorine. So that's the big improvement. Okay. All right, so that's it. Those are the 30 questions. Okay, so anything you want me to clarify about that? I know it's always easier after the fact. But... Nothing? So no other questions? So that's all I wanted to do today. So I guess any questions before we sign off then, and I'll let you have an extended weekend. I will be in touch by email about Monday. It'll likely be a lab day, so I'll give you the link of something. It'll be like a virtual lab, either a video to watch, something like that, and then answer questions, or it'll be like a little simulation that you do and then answer some questions. But yeah, just check your email for that over the weekend, and that'll be Monday's activity. So we probably won't be there won't be a live WebEx on Monday. It'll just be that lab experience. Well, one question: is the final cumulative? Yes, it is. Yeah, so it'll have questions. Actually, some will be the same questions that you've had on these midterms, or very, very similar. So it's, yeah, I know. It'll be kind of everything is that we've asked. Plus, I guess the only new material will be this next chapter. I don't know if we'll get much time to go beyond this next chapter, but really related to energy, and then maybe talking about water. But there won't be too much more new material. It'll be pretty well what we've covered. Okay. All right. Well, have a good weekend, everybody, and I'll be in contact by email about the plan for Monday. Okay, take care.